Let us solve this differential equation. It is dy by dx plus y is equal to 5. Now, what we want to do is solve it using the integrating factor method, and then also using Laplace transforms. Now, initial conditions are that y of 0 is equal to 6. So, we're going to use integrating factor method, and then we're going to use Laplace transforms. Now, what I want you to do is write it down, pause the video, and make an attempt at using those two methods. Okay, you finished? Alright, so let's look at this now. Using the integrating factor method first, you know that this equation is in the form dy by dx plus py equals q. Alright? Where p is 1 and q is 5. So, here now, what is the integrating factor? The integrating factor is e to the integral of p dx, in this case e to the integral of 1 dx, which is e to the, when you integrate 1 with respect to x, you get x, so it's e to the x. Alright? And you need to multiply both sides by e to the x. So we have dy by dx plus y equal 5. So dy by dx plus y is equal to 5. And we multiply both sides by e to the x. This is e to the x. This we have here. Let me move the plus sign over here to make space. E to the x times y equal 5 e to the x. Alright. Now, we have here the result of differentiating a product using the product rule. Now, we hold e to the x as it is here, right? And then we differentiate y to get dy by dx. Here, we hold y as it is and differentiate e to the x to get back e to the x. So you can see that what we have here is the derivative with respect to x of y e to the x. So that's the product that we had differentiated. We hold y, multiply by, differentiate e to the x, plus we hold e to the x, multiply by, differentiate y. And then that is equal to 5e to the x. Now, we integrate both sides, alright? So, we find the integral of d by dx of y e to the x is equal to the integral of 5 e to the x dx, both sides dx, with respect to x. X is the variable. When you integrate the derivative of anything, you get back that same thing. So what we have again is y e to the x is equal to, well, if you differentiate 5e to the x, is the same thing as having 5, if you integrate 5e to the x dx, is the same thing as having 5 integral of e to the x dx. When you integrate e to the x, you get back e to the x. So we have 5 e to the x plus c. Alright? Now, let's find out what y is. right? So when we divide both sides by e to the x, we get y is equal to 5 plus c divided by e to the x. That's what we get when we divide both sides by e to the x. Now, initial conditions, we had said y of 0 is equal to 6. That means when x is 0, y is 6. So we're going to let x be equal to 0 and y be equal to 6 to find c. So 6 is equal to 5 plus, remember, x is 0, so it's c over e to the 0, which is 1. This amounts to 1. So 6 is equal to 5 plus c. So when we subtract, c is equal to 1. So what we get, this is the general solution. But we know c now, so we find the particular solution. So we have y is equal to 5 plus 1 over e to the x. Good. So we've done it using the integrating factor method. Let us now look at using Laplace transforms. So we scroll back up. You know, there is only limited scrolling space downward. So let's draw a line from now and work on the right hand side of this line. All right. So here we have dy by dx plus y equal 5. This is going to be Laplace transforms dy by dx plus y equals 5. Now, we want to know what is the Laplace transform of dy by dx. What is the Laplace transform of y? What is the Laplace transform of 5? We're going to look at our Laplace transform table. Alright, so we want the Laplace transform of dy by dx. We have our table here. Scroll down to find it. Where is it? Okay. Well, in this case, they use t instead of x. Alright? T would be time, and it would be on the x-axis. Many functions vary, and they are monitored over time, so it's common to have time t being used. But our question has x in it, so we use that. So d by d of a function of t by dt, same as saying dy by dx, is s, big S of s minus small s of 0. So this is s, big f of s minus f of 0. Alright. Now, the Laplace transform of y. In our case, this y would be f of x, but they would have f of t. So let's see. The Laplace transform of f of t is what they would have. Okay, f of t is big F of s. Alright. So in this case, big F of s. The Laplace transform of 5, that's a constant. So let's see. Right? The Laplace transform of a constant here. They have us of t here. Right? us of t they have here. Now, it shows it in a kind of complicated way. But let's look at another table. If we look at this table here, they give 1. The Laplace transform of 1 is 1 over s. This makes it clearer, because here they say us of t is 1 over s, but it's really 1, right? So the Laplace transform of 1 is 1 over s. So the Laplace transform of 5 would be like 5 times 1. So it's 5 by 1 over s, so it's 5 over s, right? So in this case, you have 5 over s. Alright, so the Laplace transform of dy by dx plus y equal 5 would be the dy by dx part is s, big F of s minus f of 0, right? That's dy by dx plus y. So this would be plus big F of s, right, equals 5. So this would be equal to 5 over s. All right, so that's what we have there. Now, what we want to do is transpose so that we have f of s, big F of s, as the thing there, the subject of the equation here. So if we say s, big F of s is what we want to transpose for, minus big F of s equals, this is 5 over s. If you add f of 0 to both sides, you say plus f of 0, alright? And then what you want to do is factor out big F of s. So you have big F of s, then this would be s minus 1 inside the bracket, equals 5 over s plus f of 0. Then divide both sides by s minus 1. So you have big F of s equals, when you divide both sides by s minus 1, this will be 5 over s. The s under here will multiply by s minus 1 plus, and this would be f of, well, f of 0 divided by s minus 1. Alright? So, that's what we have so far. Now, we would want to find the inverse Laplace transform, but it's not in a way that we can do it right now. So what we have to do is use partial fractions. Now remember, for this example, the Laplace transform is going to be just about the same amount of work as the integrating factor, because it's a very simple type of differential equation. For others, it would certainly be more complicated using the other method and much simpler using the Laplace transform method. But we'll continue. Now, let's break these things up into partial fractions. Well, the f of 0 over s minus 1, that's okay. If we look at our Laplace transform table, this is like 1 over s minus a. It would fit this one, s minus a. But this one, the 5 over s minus 1, we have to use partial fractions on it. So here, what we say is that the 5 over s minus 1 is equal to, I want to break it up into two parts. A over s plus b over s minus 1. Now if you multiply both sides by s minus 1, we have 5 equals a times s minus 1 plus b times s. Then if we let s be equal to 1, what we have is 5 equals 1 minus 1, that's 0, a disappears, b times 1 is b. So b is equal to 5, alright? And then, if we let s be equal to 0, then what we have is 5 is equal to 0 minus 1, is negative 1, so that's negative a plus 0. B times 0 is 0. So a would be negative 5. Alright. So now we can write our Laplace transform. Again, big F of s is equal to a, in this case, negative 5 over s. So we have negative 5 over s plus b, which is 5 over s minus 1, then plus f of 0 over s minus 1, plus f of 0 over s minus 1. Alright? Now, we can, at this point, find our thing there, our inverse Laplace transform. Alright? Now, what is the inverse Laplace transform of negative 5 over s? Let me see something here. So, let me just check back on something. We have that, and that. This, that, and the other. Just checking back on something. The function is dy by dx plus y is equal to 5, right? And then we found Laplace transform of dy by dx is f of s minus that. So the Laplace transform of dy by dx is equal to f of s minus f of 0, right? So just double checking on something here, we'll soon continue. So we have to the n, all right. All right, so just double checking on this, and then our Laplace transform of f of y and then s. So this is what we have. So hold on, let me see something here. This is saying this should be plus, you know. It's plus f of s I should have right here. We added f of 0 to both sides, so it's plus here. So we have f of s plus f of s, right? So this should have been plus. My mistake there. Plus that. So it's s plus 1, this should be. Then we divide by s plus 1. Alright. And then this would be plus 1. Plus 1. Right. We multiply by both sides by s plus 1. So when we break this up, this part, into 5 over s plus 1 equal a over s plus b over s plus 1 it should be. When we multiply both sides by s plus 1, we have 5 equal a plus 1 b times 5, right? Then when s is 1, we said when s is 1. So this one should have been when s is negative 1. So when s is negative 1, we have 5 equal negative 1 plus 1 is 0. So a will disappear. So this would be b by negative 1. Is negative b. So b would be negative 5. Okay. And then when s is 0, we would have here 5 equals 0 plus 1 is 1, 1a. So this should be a positive a. And then a would be 5 because s is 0, b times 0 is 0. So b would disappear. You see how easy it is to make mistakes when you're doing this or any other type of math. Alright, so in this case, what we have is that a is 5 and b is negative 5. So what we have now is a over s, so it would be positive 5 over s, plus b, which is negative 5 over s minus 1. But the fact that it will be plus negative means it's minus 5 over s minus 1 plus, and then f of 0 over s plus 1. Oh boy. 5 over s plus 1, b over s plus 1. So this would be 5 over s plus 1 plus f of 0 over s plus 1. Right? So these minus, s minus should be s plus. Right? Alright, so good thing I realized that mistake there. I was feeling something was wrong somewhere. Alright, so what is the Laplace inverse of 5 over s? What you'd have to do is look at our Laplace transform table, and we see when we have 1 over s and go, remember, when we go from left to right, we're finding the Laplace transform. When we go from right to left, we're finding the inverse Laplace transform. So the inverse Laplace transform of 1 over s is 1. Therefore, the inverse Laplace transform of 5 over s would be 5. So the inverse Laplace transform of 5 over s is equal to 5. Now, what is the inverse Laplace of, let me extend this line down further. What is the inverse Laplace transform of 5 over s plus 1? Negative. It's a negative. 5 over s plus 1. So we want to see the inverse Laplace transform of negative 5 over s plus 1. This would be like the inverse Laplace transform of negative 5 times 1 over s plus 1. Right? So it's negative 5 times something. It kind of look like s. Negative 5 times something. What is it? So it would be like negative 5 times the inverse Laplace transform of this. So let's just move them. It's negative 5 times the inverse Laplace transform. Alright, it's negative 5 times the inverse Laplace transform of 1 over s plus 1. So what's the inverse Laplace transform of 1 over s plus 1? Let's see. Alright, so we have 1 over s minus a. Inverse would be e to the positive at. So if this was 1 over s minus negative a, if we make the a negative, then this would be e to the negative at. And making the a negative here would be like saying s plus a. So it's going to be e to the number times x. In this case, they use t, but we're using x. E to the number times x, but change the sign. So in this case, it's e to the number we have, that plus s is 1, e to the negative 1 x. All right? So remember, it's e to the number here, this number, x, in this case t. So we follow the same pattern. It's negative 5 e to the negative 1 x. But we don't need to have the negative 1 there, so it's just negative x. So it's e to the negative x. All right? So that's what we have. And then, what is the Laplace transform of f of 0 over s plus 1? Well, whatever f of 0 is, in this case, it would be f of 0 times e to the negative 1. No, negative x. I'm sure that that will be the case. All right? Now, here, if we write them out, if we write out these things, f of s, the inverse Laplace transform of f of s is, in that case, let's look at the inverse Laplace transform of f of t is, of s is f of t. Now, here, this is the Laplace transform of f of t is called f of s. The inverse is just f of t. So in our case, it would be f of x, which is y. We call it y. So y is equal to, now, it would be 5 minus, so it is 5 minus the inverse Laplace transform of 5 over s plus 1 will be 5 e to the negative x, 5 e to the negative x, and then we have plus f of the f of 0 part, it would be plus f of 0 e to the negative x. Now let's compare them. What we had here was y equal 5 plus, y equal 5 plus, and then we have this. Now let's simplify this first before we compare. We should really simplify it. We can factor out the e to the x, you know. So we have y equal 5. Now if we say minus e to the x, or we could say plus, you know, plus e to the x and then f of 0 first, minus, inside this bracket you have 5 and close the bracket. So we have 5 plus, factor out this bracket, e to the, well, e to the negative x, I should say, e to the negative x. Then inside the bracket, we have negative 5 here, plus f of 0 here. All right? Now, here, let's compare them now that we factor out. E to the negative x is the same as 1 over e to the x, so let's change that part. E to the negative x is same as 1 over e to the positive x. All right, let's compare. So we have 5 plus 1 over e to the x. All right? Oh, That was after we got the c. Now, before we got the c, the general solution is 5 plus c over e to the x. This is 5 plus, this would be f of 0 minus 5 over e to the x. So it's like c, the constant would be f of 0 minus 5. Alright? So if you write it out plain and straight, we run out of scrolling space, right? So we just have to work with this side, having run out of scrolling space. So y equal 5 plus, y equal 5 plus, y equal 5 plus f of 0 minus 5 over e to the x. So you have f of 0 minus 5 over e to the x. Alright, so looking at them, what we have is using the integrating factor method, it was 5 plus c over e to the x. Using Laplace transform is 5 plus this over e to the x, where this now would be like the c. Now let's apply the initial condition. What was the initial condition again? It was that when x is 0, y is 6. So y of 0 is 6. So we let x equal 0 and y equals 6. Let's see what happened here. Y is equal to 5 plus f of 0 is y when x is 0. So it would be 6. 6 minus 5 over e to the x would be 1. Right? So in this case, over 1. Now, here, what we have is that y of 0, this would be y of 0, right, over y would be y of 0. So this would be equal to 5 plus 6 minus 5 is 1. 1 over 1 is 1, right, is equal to 6. So the constant, the initial condition, would be 6, right? So what we have is y equal 5 plus, we're writing this part, where this would be the constant, the f of 0 minus 5. In this case, it turns out to be 6, is 6 over e to the x. That's the particular solution. So let's compare them. We have, oh no, not 6 over e to the x, my mistake. F of 0 is 6, so 6 minus 5. My. 6 minus 5. No, 6 minus 5 is 1, so it's 5 plus 1, which is 6. Now, when I substitute it, the f of 0 minus 5. Now, at 0, what we have is f of 0 is 6. So up here should be 6 minus 5. I left off this 5 here, 6 minus 5. So what we get is y is equal to 5 minus 1 over e to the x. Right, so that's what you should have. So 5 minus 1 over e to the x, we have 5 is minus, I say, is plus. Alright, 5 plus 1 over e to the x. If I was marking you and I see you had minus and plus, I would realize this was just an honest mistake, so I wouldn't take off any mark from it. Alright? Now, here, f of 0 is same as y of 0, is 6, so 6 minus 5. If you had put 6 up here, then I would have to be forced to take off a mark, right? But because this would have to be 6 minus 5. But if I had seen you make the same mistake of having plus, and then you suddenly put minus for no apparent reason, I would say maybe that was just a slip of the mind, so no punishment for that. No taking off a funny mark for that. Alright, so y equal 5 plus 1 over e to the x, and y equal 5 plus 1 over e to the x. So same answer for both. Alright, so here, that is a case where we used the integrating factor method to solve a differential equation, and then we use the Laplace transform method. And luckily the Laplace transform could be used, because sometimes, depending on the type of differential equation, you cannot use the Laplace transform. Alright? Now in this case, using the Laplace transform was somewhat more work, because we had to find the Laplace transform, then use what you call it, partial fractions. Then we found them, then found the inverse Laplace transform and put them together. It's just that the integrating factor method for this was less work, because it's a simple equation compared to some others. There are some other type of differential equation where it would be much less work using the Laplace transform than solving it straightforward, right? Most differential equations that are complicated, you would see that particular case. So in those cases, it's beneficial to use the Laplace transform, because it would be a lot less work. Alright, so I'll see you in the next video.